Hello again, my name is Teteje Kepsi Richie and welcome to my YouTube channel. Today our discussion on partial differential equations will be solving second order partial differential equations using separation of variables. We learn how to solve first order partial differential equations using the separation of variables. Please, if you have not watched that my video, check it out on YouTube. Today, before the video will end, I'll revise your knowledge on how to solve second order ordinary differential equations. Why are we doing that? We said that the separation of variables, after we assume that the general solution to our partial differential equation is the product function of the independent variables. When we substitute the partial differentiations, our resultant equation will be an ordinary differential equation. So we'll revise our knowledge on how to solve second order ordinary differential equations. Then we'll find solutions to second order partial differential equations using the separation of variables. This will be a very interesting engagement, so please take a seat. So if we have a second order ordinary differential equation of this nature, how do we solve? If you remember very well from ordinary differential equation, we said we should let y to be equal to e exponent maybe r of x. What do? We differentiate y with respect to x, so we say y prime will be equal to, remember when we differentiate this, we get r e exponent r of x. Then we differentiate, we need the second differential, so we get y prime equal to, when we differentiate this, we get r square e exponent r of x. What do? We substitute this into our equation. So in place of the second differential of y, we'll put this. So we get r square e exponent r of x plus this is r e exponent r of x. Then our y is what? E exponent r of x, and it's equal to 0. What is common? R of x is common to all of them, so we factor it out. So we get r square plus r, then plus 1 e exponent r of x, I factor it out, is equal to 0. We can divide both sides by e exponent r of x. Then we can get r squared plus r plus 1 equal to 0. Now this has become a quadratic equation, which we can easily solve to get the values of r. And when we get the values of r, our complementary solution will depend on the values that we are getting for r. If you remember very well, we said that we can get two real and distinct roots, we can get two complex roots, or we can get two repeated roots, if you remember very well. And there is a solution to each of these roots. So now, when we have two real and distinct roots, what is the complementary solution? When we have two complex roots, what will be the complementary solution? And when we have repeated roots, what will be the complementary solution? That's the next thing we'll talk about. So, when we solve our resultant quadratic equation, we get two values. And we're saying that the two values can be two real and distinct roots. So if there are two real and distinct roots, then our complementary solution y will be equal to maybe c1 e exponent alpha 1, that's lambda 1x, then plus c2 e exponent lambda 2x, if you remember very well. That's when we have two real and distinct roots. So that's the first one. The second one, we can have a situation where our lambda 1 is equal to lambda 2. So then it becomes repeated root. And when it is repeated root, our complementary solution y will be equal to c1x e exponent alpha, since they are equal, alpha x, then plus c2 e exponent alpha x, if you remember very well. So this is two repeated root. Then we can also have the third one, the complementary solution, y to be equal to e exponent alpha x bracket c1 cos beta x plus c2 sine beta x. That's when there are two complex roots. Where the lambda is the real part of the complex root. Where the lambda is the real part of the complex root. And the beta is the coefficient of the imaginary part, if you remember very well. So now, this is the three situations that may occur. Now remember, this is called a discriminant from our quadratic equation. And we said that if the discriminant, remember, is in a square root, if you remember very well. If the discriminant is less than, okay, the discriminant, that's b squared minus 4ac, okay, is greater than 0, then there will be two real and distinct roots, if you remember very well. Then if the b squared minus 4ac, that is discriminant, that's b squared minus 4ac, is equal to 0, then there will be repeated roots. Then if it is less than, that's b squared minus 4ac, okay, is less than 0, then there will be then the roots are complex, if you remember very well. So with this our knowledge and this, we can be able to find solution to partial differential equations using the method of separation of variables. So we take example questions, then we see how we deal with it. So let's look at our first question. It's a find a general solution to the partial differential equation del square u over del x square minus 2 del u over del x plus del u over del y equal to 0 using separation of variables. So remember, we said the idea behind the method of separation of variables is that we assume that the general solution to the partial differential equation is the product of the independent variable, the product function of the independent variables. So for the sake of time, we can rewrite this as x, y, x, y. So now we find del u over del x. So the partial differentiation of u with respect to x. What do? We keep the y constant. So we get x prime of y. Since we have second differential, we differentiate again. So I'll differentiate this again. We get del square u over del x square. So this will be x prime prime y. Now we find the partial differentiation of u with respect to what? Y. So the x will be kept constant. So we have del u over del y will be equal to, the x will be kept constant. So we have y prime of x. So what next? We substitute the second differential of u with respect to x, and if the differential of u with respect to x, and then differential of u with respect to y, to our partial differential equation. After that, it will become easily separable. And when we separate it, it will become an ordinary differential equation. So now let's substitute that and see. So in place of del square u over del x square, we put x prime of y, x prime of y. So minus 2, our del u over del x is x prime y. Then our del u over del x is, so plus y prime x equal to 0. So what do? We can send the y prime here. So we have x. So our x prime y minus 2x prime y will be equal to negative y prime x. So what do? We can divide both sides. We can bring the y out since it is common. So we have x prime prime minus 2x prime times y equal to negative y prime x. When we divide both sides by xy, so here by xy, there by xy. This y will deal with that y, so we have x prime prime minus 2x prime all over x will be equal to the x will also divide the x. We'll have negative y prime over y. And remember, we said it should be equal to a constant, let's say lambda. Now, how do we do that? We take each of these, equate it to lambda, if you remember very well, and solve. So this, we equate this to lambda, equate this to lambda again, and find the solution, the function x and the function y. Then we substitute into this to get our general solution. Okay, so we take each of them, equate it to the lambda. So we have x prime prime minus 2x prime over x equal to lambda for the first one. So we can get x prime prime minus 2x prime equal to lambda x, on cross multiply. You can rewrite it as x prime prime minus 2x prime minus lambda x equal to 0. Then this is an ordinary differential equation, a second order ordinary differential equation. This lambda x actually. So now how do we solve that? So we assume that x is equal to e exponent maybe r of t. So we differentiate x with respect to the t. So now our x prime will be equal to r of t. Then our x prime prime will be equal to r squared. We differentiate this again, so we get r squared er of t. This is from ordinary differential equation. So now we substitute. We get, in place of this, we get r squared e exponent r of t minus 2r e exponent r of t. Then minus lambda e exponent r of t equal to 0. So what we do, we can factor out e exponent r of t out. So we get r squared minus 2r plus lambda, okay, minus lambda, okay, e exponent r of t equal to 0. When we divide both sides by e exponent r of t, our r squared minus 2r minus lambda will be equal to 0. So now we solve this quadratic equation to know the nature of the roots. So we can complete square and use this, but I want to use the r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now what's our a? Our a is the coefficient of the quadratic term here, so it's 1. Our b is negative 2. And our c is equal to negative lambda. Is the constant. So we substitute. So our r will be equal to, so when we substitute negative 2, we get 2, because the negative will affect, plus or minus the square root of negative 2 square will be 4 minus 4, a is 1, so 1. Then c is negative lambda, okay, all over 2a, and 2, 1, the a is 1. So our r will be equal to 2 plus or minus the square root of 4, this will become plus, so plus 4 lambda all over 2. What do we have? We can factor out 4 here, so we get 2 plus or minus the square root of 4 out, 1 plus lambda all over 2. When we find the square root of 4, we'll get 2. So our r will be equal to 2 plus or minus 2 the square root of 1 plus lambda all over 2. So when we divide this, we'll get 1 there. So 1 plus or minus To divide this, we get 1, so the square root of 1 plus lambda. So we get r to be this. So our r can be equal to 1 plus lambda, the square root of 1 plus lambda, or 1 minus the square root of 1 plus lambda. So we have two distinct roots. Now, however, then the value of lambda will determine the nature of root that we'll get here. The value of lambda will determine the nature of root. Since this is a complete second order, we'll leave it like this. But when we go further to find the value of lambda in our subsequent one, we'll be able to know whether it is a complex root, two distinct roots, or two repeated roots. So this one, let's assume is two repeated roots. Okay, two repeated roots. So our complementary solution, y, will be equal to, okay, since it's a function of x, so x will be equal to c1, okay, e exponent 1 plus lambda, okay, x, then plus c2 e exponent 1 minus 1 plus lambda x. So this becomes a function of x. This becomes a function of x. Now you equate this to this. Remember, this is just a first order, so it will be easy to solve. Easily separable, first order ordinary differential equation. We find that, then we substitute it into this. So we solve our second part of the y, or the function for y. So we can multiply both sides by negative. So we get y prime over y equal to negative lambda. What do? We can rewrite this 1 over y prime equal to negative lambda. Then we integrate both sides. So the integral of 1 over y lambda, 1 over y prime equal to integral negative lambda dy. When we integrate this, we get lim y. And to be equal to, this is nothing but a constant, so negative lambda y plus our constant of integration. Remember, lim is a natural log, a log with a natural base e. So our y will be equal to e exponent negative lambda y plus c. So we let c to be equal to capital. Okay, we can rewrite this first. So y will be equal to e exponent negative lambda y times e exponent c. Then we let the c to be equal to capital C1. So our function y, okay, will be equal to C2. Since we have C1, C2 here, we let this be C3, okay, C3. So we have C3 e exponent negative lambda y. Then this becomes our function of y. So since we know our function of x, we know our function of y, we substitute into this to get the general solution to this second order partial differential equations. So we have the function of x to be this and the function of y to be that. So we just substitute that to this to get our general solution. So our general solution, u of x, remember we said it's a function of x multiplying a function of y. So our general solution then, u of x will be equal to the c1 e exponent 1 plus the square root of 1 plus lambda x plus c2 e exponent 1 minus the square root of 1 plus lambda x. That's for the x, the function x, times the function y. And what is the y? The y will be, let me clean it so that I can rewrite it for you to understand. So now we substitute to get our general solution. So our u of x, y will be equal to a function of x. What's the function of x? Is c1 e exponent 1 plus the square root of 1 plus lambda x plus c2 e exponent 1 minus the square root of 1 plus lambda x. That's for the x. Then times the y. What is our y? Our y is c3. So c3 e exponent negative lambda y. Then this becomes our general solution to this partial differential equation using the method of separation of variables. We'll solve one more question where boundary conditions or initial conditions are given. Then we'll see how we deal with that. So let's solve our second question where some boundary conditions are given. They say find a particular solution to the PD, the partial differentiation of u with respect to x twice equal to half the partial differentiation of u with respect to y, given these boundary conditions. So how do we solve that? So we are going to use the method of separation of variables to do this. Now, with the method of separation of variables, we assume that the general solution to this is a product of the function of the independent variables. So for the sake of time, we can rewrite this as x, y. So what do we need? We need a partial differentiation of u with respect to x twice. So we have the partial differentiation of u with respect to x will be equal to x prime y. And the partial differentiation of u with respect to x twice will be x prime prime y. What do? We find the partial differentiation of u with respect to y. So the partial differentiation of u with respect to y, x will be held constant. So we have y prime x. So what do? We substitute the partial differentiation of u with respect to x twice to this. Then this to that. We substitute. Then it becomes easily separable, and for that matter, a second order ordinary differential equation. So now we substitute. So in place of that, we get x prime prime y equal to half y prime of x. So when divide both sides by xy, we get x prime prime over x will be equal to half y prime over y. And we said this should be equal to a constant, let's say lambda. Then we take each of them equated to lambda. So we have x prime prime over x equal to lambda first. So we have x prime prime equal to lambda x, which can be rewritten as x prime prime minus lambda x equal to 0. This is a second order ordinary differential equation which can easily be solved. So now, what do? We know that we let x to be equal to e exponent maybe r of t. What happens? When we have x prime, we get r e exponent r of t. That means we are differentiating this with respect to t. Then our x prime prime will be equal to r squared e exponent r of t. So now we substitute this into our ordinary differential equation, this. Then in place of x prime prime, we substitute that. And in place of x, we substitute this. So what do we have? We have r squared e exponent r of t, okay, minus lambda e exponent r of t equal to 0. So we can factor out that. So we get we factor out e exponent r of t equal to 0. When we divide both sides by e exponent r of t, we get r squared minus lambda equal to 0. Now, the value of lambda here. Now, the value of lambda will depend on three things. First, lambda can be equal to 0, lambda will be greater than 0, or lambda will be less than 0. So that we'll get the possible roots. So when lambda is 0, we get r squared minus 0 equal to 0. So our r squared can be equal to 0. r will be equal to the square root of 0. Then we'll get the value of 0. The square root of 0 is 0. But remember, the square root of every number is plus or minus. So that's 0 repeated. So we have a repeated root. So in a situation where lambda is equal to 0, we have a repeated root. Then our solution for x in that case will be repeated root. So we have c1x e exponent 0x, if you remember, plus c2 e exponent 0x. So s of s, 0 times s is s. E exponent 0 is 1. So we have c1s plus c2, the same for that. So this is a situation where lambda is equal to 0. So now we'll find a situation where lambda is, let's say, greater than 0. Why is greater than 0? Because we want to solve this easily. We should say that lambda is equal to a positive k square. That means any number we square there will be greater than 0. So now what we do, we substitute. In place of lambda, we put k square. So you have r square minus k square will be equal to 0. R square will be equal to k square. On find square root of both sides, our r will be equal to the square root of k square. R will be equal to plus or minus k. So these are two distinct roots. Then our function there, our x, will be equal to c1 e exponent kx plus c2 e exponent negative kx. Then now, a situation where our lambda is less than 0. What happens? We let lambda to be equal to a negative number square. So what we do? We let it be equal to that so that it can be it will be easy to solve. So now we substitute. So we have r square in place of the lambda, we put the negative k square. So we get plus k square equal to 0. So our r square will be equal to negative k square. So when we find the square root of both sides, our r will be equal to the square root of negative k square. And remember, this will be equal to plus or minus ki, complex system, where the real part of the complex system is 0. Okay? And the imaginary part, the coefficient of the imaginary part is k. Then our x there will be equal to c1 cos kx plus c2 sine kx. All this from ordinary differential equation. It should be bracket e exponent, the coefficient of the or the e exponent, the real part, but the real part is 0, so e exponent 0 will be 1. It will be the same thing. So now this is when lambda is less than 0. So we have three situations. First, when lambda is equal to 0, we have this. When lambda is greater than 0, we have this. And when lambda is less than 0, we have this. Three systems. Now we take the other aspect, the y aspect, and find the solution to that aspect too. So now we have found all the possible solutions to the x. Now we need to find y. So because we change everything to k, we let this to be equal to k. So we say half y prime over y should be equal to a constant, let's say k. What we have, we can multiply both sides by 2. So we get y prime over y equal to 2k. You can rewrite this as 1 over y prime equal to 2k. We integrate both sides. We integrate dy. When we integrate this, we get ln y equal to 2ky plus our constant, let's say c. So we can rewrite this as, one, we know this is a natural law. So we say y is equal to e exponent 2ky plus c, which can be rewritten as e exponent 2ky times e exponent c. So now we let e exponent c to be equal to c3. Okay, since we have c1 and c2 here, so our y will be equal to c3 e exponent 2ky. So now remember we said our solution, our general solution, is a function of x multiplying a function of y. So what do? We just find those functions. So our general solution will be equal to, see, we have a function of x here to be c1x plus c2, okay? Then a function of y, which is c3 e exponent 2ky, okay? Where our constant lambda is actually equal to 0. Then the second one, our function s is what? c1 e exponent kx plus c2 e exponent negative kx, then times our y, which is c3 e exponent 2ky. Remember, when lambda is actually greater than 0. Then the third one, we have c1 cos kx plus c2 sin ks, then times our c3 e exponent 2ky. So this becomes our general solutions. That's depending on the values of the constants. Now what happened? We'll look at the boundary conditions given to us and see that which of these solutions satisfy the boundary condition. Then we take that and find a particular solution to our partial differential equation. So looking at our boundary conditions given to us, you will see that this boundary condition actually satisfy this third solution, the third solution. So we take the third solution and find a particular solution to that. Then that becomes the particular solution to our partial differential equation. So now we'll copy that, then we'll try to substitute the boundary conditions to it to find a particular solution to our partial differential equation. So now we substitute our boundary conditions. The first one, u of 0 y equal to 0. So in place of x, we put 0. So we have c1 cos k times 0 plus c2 sin k times 0 times c3 e exponent 2ky is equal to 0. So what do we have? This will be 0. K times 0 is 0. Cos 0 is 1. 1 times c1 will be c1. Sin k times 0 is 0. Sin 0 is 0. Times c2 will be 0. So we have c1, c3 e exponent 2ky equal to 0. We will make c1 excited by dividing both sides by c3 e exponent 2ky. When we do that, our c1 will be equal to 0. So we substitute our c1 into this our general equation. So we will now have u of xy is equal to, in place of that, we get 0 times cos kx plus c2 sin kx, okay, times c3 e exponent 2ky. What happened? This will be 0, so it will be. We have our general solution being c2 sin kx, then times c3 e exponent 2ky. So now we substitute our second boundary condition, this into this. So in place of x, we put 3. So we have, this will be c2 sin So 3k, then C3 e exponent 2ky is equal to 0. We can divide both sides by C3 e exponent 2ky. We have C2 sine 3k is equal to 0. We can divide both sides by C2. So we have sine 3k is equal to 0. How do we find k? Our 3k will equal to sine inverse of 0. Sine inverse of 0, okay, will be equal to pi n, multiples of n. Pi, remember, in radius is 180 degrees. Sine 180 degrees times any figure will give you 0. So where n is equal to 1, 2, 3 to infinity. So now what is that value of n? That's what we find. So our k here will be equal to pi n over 3. So now we know k. We substitute k into this equation. So we have u of xy is equal to c2 sine, in place of k, we'll put pi n over 3x. Then c3 e exponent 2 pi n over 3y. So this is what we are having. Now we substitute our third condition. So we have this. Now we substitute our third boundary condition. So in place of y, we put 0. If you can see, you see that. Then we equate it to 5 sine 4 pi x. So what we have c2 sine pi n over 3x. Then c3 e exponent 2 pi n over 3 times 0 will be equal to 5 sine 4 pi x. So the whole of that will be 0. So e exponent 0 will be 1. We'll have c3 there. So we can say c3, okay, c2 sine pi n over 3x times our c3, because e exponent 0 is 1. It will be equal to 5 sine 4 pi x. What do we have? I can let this multiply this. So I'll get c2 times c3 sine pi n over 3x is equal to 5 sine 4 pi x. So this we just compare. You see the coefficient here is c2, c3, and the coefficient there is 5. So we can say that our c2 times c3 will be equal to 5. Then also the variable, the x here, you can see x. So we can say the coefficient of the x there are equal. So we can say pi n over 3 is equal to 4 pi. What do? We multiply both sides. So we have pi n will be equal to 12 pi. When we divide both sides by pi, our n will be equal to 12. So n actually is 12. What do? We substitute our n equal to 12 to this to get our particular solution. So now we know our c2, c3 to be 5 and our n to be 12. So we substitute that. I'll bring the c3 to multiply this c2. It's still the same. Then I'll substitute 12. So I have u of xy, okay, equal to c2, c3 sine pi, our n is 12, so 12 over 3x, okay, then e exponent 2 over 3 pi times 12, pi times 12y. So we have e exponent 2 pi times 12 over 3y. So in place of n, we put 12. What we have? We have u of xy. Remember c2, c3 is 5. So 5, 3 divided, remember there is x here. 3 divided by 12 is 4. So we have sine 4 pi x. Then e exponent 3 will go into 12. 3 will divide 12 4 times. 4 times 2 will be 8. So 8 pi y. Then this becomes our particular solution to that our second order partial differential equation. So I hope you get this. Play over the video and I know you get a concept. Remember to subscribe to the YouTube channel and click on the notification bell so that anytime I post a video, you'll be the first to receive it. Until we meet again, bye-bye.